Thank you so much. It feels so good to be here. Thank you everyone for being here. And thanks to those of you who have logged in virtually. I really appreciate your time and interest. I'd like to thank Dheeraj and Santosh for making this event happen. And thanks again for this opportunity. So the next 30 minutes or so, I'm gonna briefly tell you a story of melting ice and rising oceans in warming climate. But I was also asked to briefly reflect on my journey from Nepal to NASA. So I'm gonna spend my first 5-10 minutes to walk you through my career trajectory. Okay, not the PC guys, so somebody has, okay, it's working, cool. So I was born and raised in Rhinos municipality in Lamsung. Here you could see a beautiful image of Rhinos Valley that I took a few years back. And there's a famous Rhinos cult. It's been pretty famous lately. And if you haven't visited this place, I highly recommend to go and spend some time there. And if you are from this part of Lamjung, so you should recognize JPL went from this side to that side. But anyway, so my village is somewhere down here in the foothills, and my dad was a high school teacher, so it was natural for my brother and me to go to local high school, and that's where I completed my high school from. And then I joined Ascal campus to do my intermediate in science and physics. So I'm from the era where when +2 and all those things were not or just barely started. Anyways, then I got a scholarship to do my bachelor's of engineering from IUE, Purvanchal campus in Durham. So I did my engineering in agricultural engineering. So I am proud to be part of the first batch of agricultural engineers that Nepal has ever produced. And I'm so excited to see some of my engineering colleagues sitting down there. So good to see all of you guys. Then when we graduated in late 2004, early 2005, the situation in the country was so dire because of decade-long Maoist insurgency. And it was virtually impossible for us to find any reasonable job in Nepal. And most of us were trying to look for the opportunity to do further studies, mostly from foreign institutes. And I was very lucky to, sorry, it's not. Somebody help me, please. So I was very lucky to get a scholarship to study. Oh, there you go. Well, thank you. So I got lucky to get a scholarship to study Masters in Engineering Geology from a couple of institutes in Belgium. So it was an inter-university program jointly hosted by University of Ghent and Vrije Universiteit of Brussel. So it was when I was doing my master's research in engineering geology, so I was very much fascinated by the beauty of snow and hence glaciers and the majesty of Himalayas, and I wanted to do some research that is related to Nepalese Himalayas. And that's when I was formally introduced to this wonderful field of geophysics and climate science in general. So here for me, the motivation at the time was the series of pictures that you could see. So these are some snaps for glacier AX010. And you could clearly see the glacier was looking pretty healthy back in 1978, but over the course of 20 years, the glacier was already detached from, it was shrinking by quite a bit, and there is even, you could see the formation of Progressive Lake, and we all know how important and how critical the glaciers are, both from opportunity and hazards perspective. And so coming from engineering background with reasonable strength in mathematics, so I was interested in modeling the glacier flow dynamics. And here you could see the prediction of this particular glacier. You could see glacier length as a function of time and under different climate change scenarios. And so basically, the long story short here, I predicted back in 2009 that this particular glacier is very, very less likely to survive beyond 2060 or so, no matter what climate change scenarios that we as a humanity gonna choose. Okay, so again, intrigued by the beauty of glaciers and the mathematical skills that I could apply to understand glaciological processes. Then I had an opportunity to do Ph.D. in theoretical glaciology. So this is when I tried to diagnose the so-called governing equations of glacial flow, which is essentially the fluid flow problem. And I tried to understand different processes that play roles in driving and controlling glacial flow. And here you can see the glacier is a block of ice flowing from left here to the right side. And it's mostly driven by the gravitational gradient. And there are several processes that try and control the glacial flow. And I tried to kind of dissect, all these processes. And the end goal was that because if you want to capture all of these processes in a comprehensive manner, then the model that we end up with would be significantly, it's going to be a massively computationally costly models. And the idea was to try and find a balance between not missing too much physics, but at the same time not having, too big a model that we could not simulate for even a few years into the future. But anyway, at that time, my PhD work was recognized by the University of Colorado Boulder as the best PhD thesis award, which was basically, they awarded naturally annually, and so they try to, collect the PhD thesis submission from the previous year on the topic ranging from all surface processes to the interior geophysics of the planet. And as a young researcher, it was really a big deal for me. It really gave me confidence and sort of feeling that I truly belong to the forefront of geoscience and climate science that we view from the Western world or NASA in particular. So then afterwards, I got an opportunity to join Jet Propulsion Laboratory, the first California Institute of Technology, and then Jet Propulsion Laboratory as a postdoctoral researcher for 3 years in total. And this is when my view towards science has radically changed. I used to be so focused on a teeny tiny problem of geophysics, a bigger picture of our system sciences. And now I was introduced to try and see things in a broader perspective. So now I mostly study glaciers and ice sheets as part of the Earth system. And in particular, I try and understand the interactions between the atmosphere, solid Earth, sea level, and ice sheets across time scales. So for those of you who is not familiar with Jet Propulsion Laboratory, so Jet Propulsion Laboratory is a laboratory of California Institute of Technology, and it's been fully funded by NASA. So basically we are NASA scientists working at Caltech or Caltech employee working for NASA. It goes either way. And here is a picture of the first director of Jet Propulsion Laboratory, who was a Caltech professor, and I think it was founded sometime in 1940s or 50s, I even forget that. But even before it was formally founded, some of Caltech scientists and faculties used to do the propulsion experiments, and they were sent to foothills of San Gabriel Mountains, if you have been in this part of the world. And this is a picture from 1936 of some researchers doing their lab experiments there. And it's the exact same venue that has been transformed into such a beautiful campus of present-day Jet Propulsion Laboratory. And yeah, and we all know that Jet Propulsion Laboratory is a premium institute for robotics and space exploration. And JPL has explored virtually all of solar system's planets and many of moons and comets and asteroids and so forth. And JPL has led all successful rovers that has ever been sent to Mars. And here's a nice poster of the Perseverance rover that was launched in 2020. And for the first time from Jet Propulsion Laboratory, some of the engineers have managed to fly a helicopter in extraterrestrial space, in this case in Mars. So this is really an inspirational place actually, and if you try and for me it's more like a spiritual. When I go to Jet Propulsion Laboratory and work for NASA, it's much more than doing science. It's more about inspiration. It's more about humanity, and it's more about thinking beyond the day-to-day life problems that we deal elsewhere. So here, this image, also again from NASA, shows a bunch of satellites that have been orbiting our planet to understand and study the Earth as a system. And so we have a bunch of satellites. They are dedicated to measure a wide variety of observables, be it from atmospheric composition to biomass changes, or from ice mass changes to sea level rise, and you name it. So we try and observe virtually all possible physical aspects of our planet. And again, the end goal is to try and understand the working mechanism of our planet as a system. And for this particular presentation, the most relevant satellites are shown in here. And of course, I don't want to name all of them, but back in 1992, Topex Poseidon was to measure the change in sea surface height. And since 1992, there have been 6 missions, I think 7 or 6 missions that have launched to try and continuously observe the state of the sea surface height. And here, the SWOT, surface water, sorry, I forgot, I should remember the name. I think sea and water, surface water and ocean topography mission. So that was, the latest of the Ultimate series. And here you can see, so basically this mission maps it's a radar interferometry technique. So basically it measures the two-way travel time between the satellite and the surface of the underlying ocean. And so we keep on measuring that. And now since 1992, we have a continuous measurement of global ocean sea surface height change. So how does the end product of this of those data look like? And here you can see the change in sea surface height relative to 1992. So that was the first time we had such observation covering the whole planet. And relative to 1992, I think in virtually it's a difference between 1992 sea surface height and the present day sea surface height. So here you can see the red shade means the surface has risen, and blue means it has fallen. And as you can see, sea surface or sea level you may call has risen virtually everywhere. And in some places where you see really dark red patches, and that's where sea level has risen by significantly. If you can't read the number here, so this number is about 15 centimeters. So another way of looking at the same data is if we accumulate, or if we integrate, or not integrate, if we average out the global mean change in sea level and plot as a function of time, here is what it looks like. So from 1992 to present day, the global mean sea level variation is evolving, as you can see in here. The units are in millimeter, and if you feed a simple linear trend line, so what you see is the fact that global mean sea level has been rising by about 3.5 millimeter every single year. So now just to put things in context, how big is this number? And the short answer is significantly big. And to back up this statement, here I show the sea level rise by century during the Common Era. So you could see the first century through 20th century. So in the first centuries, the cumulative sea level change was about a couple of centimeters. So these are in centimeters. And you could see all those towers here. So in those centuries, the sea level, the gain in sea surface height was positive, while in the other years, they were negative. And if you imagine a line drawing all the peaks and troughs here, then what you could basically see is what you call the natural variability in sea surface height change. But something dramatic happened in the 20th century. And here you could see during the 20th century, sea level rose, but not by, but by quite a bit. So it's almost about hitting 15 centimeters. So that is a significant amount of sea level rise that happened in 20th century. But the scary part is that we are only into the 22nd years of this century, the 21st century. And the tower is already catching up with the total change in sea level that happened in the previous century. And so of course there are a lot of uncertainty in terms of projecting sea level, and I'll briefly touch upon this, that topic in a bit. But we scientists believe that it is very much inevitable that the sea level is going to hit 1 meter just in this century. And so roughly that's the order of magnitude that we are looking for. And just extend this tower, and we are literally reaching over there. And it's a really scary thing. And I'm not even talking about what might happen in the following centuries, which I will touch upon in a bit. And we know that these tall two towers that we saw in the previous century and this century is because of human-induced climate warming. So it is us who are to be blamed for what is happening in the global ocean. And here is a quick, quick proof that human-induced climate warming is responsible for the 20th and 21st century sea level rise. So what you see here is again global mean sea level in millimeter per year as a function of time during Common Era, and all you see the natural variability. So basically all the towers that you saw in the previous slides is essentially the cumulative data by each century, by centuries. And again, you see the part of natural variability, and here is what is defined in this particular paper as the inception of the industrial era, 1700 CE, and then it has started really taking a big leap in terms of increasing global mean sea level. And in this particular plot, on the right side is the probability, so which is basically the probability that this rise in sea level is because of what we did since the inception of industrial era. So basically, the amount of CO2, the burning of coal or other fossil fuel. So we have really, everybody knows about global warming and the basic mechanism, basic working principle of global warming. So it's because of that increase in global temperature. Then, because of that, we have to go through such a big leap in global sea level change. And we're confident that this emergence of human-induced sea level rise happened as early as 1873 with 95%, with a probability of 0.95. Okay, so now what actually happens when we raise temperature of a planet like of Earth, and what are the physical processes that connect the rise in global temperature to the rise in global mean sea level? And there are primarily two different processes. The first one is what we call the thermal expansion. It's basically a story of fire and ice, as you can see here. So basically, on one hand, we have literally put fire, meaning we have literally put more heat to the ocean system. So in fact, more than 90% of the human-induced global warming or human-induced increase in planetary temperature or heat has been observed by the ocean. And what happens when we heat water is that it simply causes, at the atomic level, it simply causes the water molecule to jiggle faster than in the previous cooler state. And in doing so, the volume of the ocean water increases, and that's precisely what happens in thermal expansion. And the other aspect of other process that connect global warming to sea level rise is via melting of land ice. So by land ice, I mean all the global glaciers, including those that we have in our Himalayas, to the Antarctic ice sheet and Greenland ice sheet. And if you melt water from land, so eventually its fate would be to get into the ocean and hence causing the sea level to rise. And it's not just a hypothesis. We have shown, in fact, I have contributed to this paper that came out in 2020 in Nature, where we have shown for the first time that by combining the thermal expansion and what we call the ocean mass change that literally comes from land, and we can show that throughout the 20th century, since 1900 to present day, so we can reconstruct the observed global mean sea level change. So in blue you see the observation of global mean sea level, and if you could recall from a few slides back, the satellite altimetry only covers since 1990 or so, but there are the tide gauge stations and so forth that could be used to extend the satellite measurements all the way back to 1900, and some people even go back to 1850 or something like that. But anyway, so we have the observation, and the black one is model reconstruction, which is essentially the sum of the ocean mass change, which is this line, and the thermal expansion. So this is proof that it's not a mere hypothesis that thermal expansion and the contribution of land ice causes sea level to rise, but we have demonstrated here in this paper. And just to sum things up, in the recent time, here the composition of how much has been the contribution from mass change and how much has been the contribution of the thermal expansion. We call it static. The residual is pretty small, that we can, by summing those two components, we can explain the observed data within the data uncertainty. And the mass contribution can be further broken down into three major contributors. Again, and all of those are related to ice. So we have glaciers, which is really a big component at the moment, and it will remain a relatively big contributor for the next 40, 50 years until we will be running out of the glacier ice in first place. And then Greenland is equally as a big contributor at the moment, and Antarctica is slowly catching up. How am I doing with time, Santoshi? Okay. So now, being a cryospheric scientist, I want to focus now on this mass contribution to the sea level, and which is essentially the story of ice and ocean mass exchange. So how do you measure the change in mass in glaciers and ice sheets? So there are many methods, but one relatively direct method is what we call the Gravity Recovery and Climate Experiment GRACE and its follow-on mission. So in these missions, so we have a pair of satellites that are orbiting our planet in tandem. And so what we measure is basically, we measure the difference in distance between the two satellites, and which can be directly related to this change in gravitational anomaly underneath the satellite system. And in a relatively short time period, this change in gravitational anomaly could be linked to this change in water height, or change in the water storage or the ice storage. And this is how we infer the change in ice mass, for example. So here's an example of the Greenland ice sheet mass change. So on the left-hand side, you could see the thinning of the ice sheet. There is no thickening, so it goes from plus 0.5 to minus 5, and all red means the ice sheet has been thinning virtually everywhere in the ice sheet, especially along the coastline. And here you can see the cumulative change in mass from the ice sheet. So beginning in 2002 April, the ice sheet mass was some arbitrary amount, and relative to that number, then surely and steadily, the ice sheet has lost so much mass to the ocean. Actually, it is about 280 gigatons every single year. So gigatons is 1 gigaton is 10 to the 9 cubic kilometer of ice, or kg of ice, I think. And so with 1 gigaton, sorry, if we lose 360 gigaton, that would be sufficient to raise global mean sea level by 1 millimeter. Or other way of looking at this image is that I think 1 gigaton of ice, if we melt it, it's gonna be sufficient to fill out 400,000 of Olympic swimming pool, something like that. I might be wrong here, but it's a massive amount of mass. And the same thing for Antarctic ice sheet, but it is a bit of, because it's in the southern pole, which is arguably the coldest and the driest part of the planet. But already you could see initially not much was happening, but beginning about 2007-8, and it had also started losing mass. So overall, the linear rate of mass loss is approximately half of that of Greenland ice sheet. And you could see significant melting happening in the Right.
Sun minus, right? Duplicate. Is we actually in slice flow. Oh, good. Thank you. Good.
Okay, so basically here, unlike in Greenland ice sheet, so most of mass is being lost from what is called the N-SLCT sector, and this is where, what journalists like to call a doomsday glacier is located, and the glacier is called, actually we call it Poets Glacier. If one glacier over here, which is really prone to irreversible collapse in the next couple of centuries, if it melts, the single glacier alone, it will raise the global mean sea level by about 2 meters. The global sea level would rise by about 2 meters. And for Antarctic ice sheet, there is some accumulation of mass in here, which is mostly because of increase in precipitation. But again, the wholesome story of the ice sheet is that it has been continuously losing mass. And this is a rather complicated looking picture of glaciers. I think Santoshi and Dhirajji, they work more on glaciers than I do, but the main point that I want to show here is that all these circles here would imply that the glaciers all over the planet have also been melting. So the numbers are negative everywhere. And especially in the Himalayas, this little square here you could see, if you sum those three numbers, so we find that there has been about 20 gigaton of mass being contributed to the ocean, the global mean sea level rise every single year since 2000 to 2002. So how do glaciers and ice sheets evolve in the future? And here, there are a couple of snaps from the latest IPCC report. And I don't want to take a particular number associated with this glacier, but the thing that I want you to focus on is the fact that there are a bunch of models of varying degrees of complexities, and there are some of the models can capture some what you call the higher order physics of ice flow, while others cannot. And the model forcing parameters are not also necessarily precisely the same. So there are so many rooms of uncertainties. But the main story here is that the projection is really, I mean, if you really think of the probability of what might happen, it's really a spread out probability distribution function. And basically you see the projection as a function of time again, you see the end of the 21st century. And so is also true for Antarctic ice sheet. And if you could see, there are a couple of lines here that really go down here. And I will briefly touch upon why Antarctic ice sheet is extremely difficult to model compared to Greenland ice sheet and many other glaciers. And the simple answer is that the part of the ice sheet is residing on the bedrock that is below the present-day mean sea level. And here you could see the bathymetry of the ice sheet. So basically, if you remove all the ice from the Antarctic ice sheet, and this is what you see. So you see a big giant mountain range here that has elevation of, actually it goes all the way up to 3 kilometers or so. And at the same time, the western part of Antarctica, and also in this part of East Antarctica, and virtually everywhere, as you can see, the blue color implies that if we remove the ice instantly from the ice sheet now, then this part will be the part of the ocean, because the bed is well below the mean sea level. And it's so much low that it could go down to 3.5 kilometers below the mean sea level. And so what happens and we call this ice sheet that reside on this bedrock that lies below the mean sea level, we call those portions of the glaciers the marine ice sheets. And there are a bunch of processes that have been kind of controversial in that whether these processes really are operating in the Western Antarctic ice sheet. That's a whole different discussion. But here I'm highlighting two critical processes. One is called the marine ice sheet instability, and it is only applied to retrograde slope, which means that if ice is flowing this way, the slope is deepening towards the interior of the ice sheet. So what happens in here is that if glacier starts melting, then it finds its terminus in the much deeper trough. And that's where the flux of the ice increases. And it kicks in, it kind of reinforces the positive feedback loop. And once the glacier starts retreating, it is going to go downhill. And that's what happens in this particular area. And that's why a glacier, biggest glacier in this region is called a doomsday glacier. And this is a relatively recent concept. And I personally, I didn't buy this idea, but it's really a controversial process, which is related to, what is called is marine ice cliff instability. So the idea here is, for this process to happen, it does not have to be retrograde slope. It can be, it's independent of retrograde slope. So basically what happens is, once the ice shelf, the floating part of the ice, breaks, then the ice sheet all of a sudden finds a much taller cliff than it could be physically feasible. And because ice cannot, the viscous flow of ice cannot keep up with this sudden breakup of the cliff, then the cliff has to go through the brittle failure. And again, once the process kicks start, because the ice is generally thicker in the interior side, and the height of the cliff starts increasing. And it also reinforces this positive irreversible ice mass process. But anyway, so because of this, you could see the projection of sea level here. This is the global mean sea level projection for the 21st century. I pulled out from IPCC, and you could see a bunch of models under various climate change scenarios are shown here, but I don't think I can read it here, but what it literally says is that the low likelihood, high impact storyline, including ice sheet instability process, cannot be discarded under SCP 8.5 scenarios, SPS 8.5 scenarios. And if you extend the projection back to 2300 AD, which is nearly 200 years from now, the projection looks really scary, and it could be that we might end up having a 15 meter of global mean sea level in the next 2 centuries. So it's a really scary thing, but the take-home message here is that with full confidence I can tell that the multi-meter sea level rise is inevitable, even if it's not, it may not be 15 meters, but 1 or 2 or 3 meters of sea level rise is inevitable in the next 150 or 200 years. Okay, so now I have, so these are the things that I usually don't talk about. Being a scientist, we are on the science side of things. But let me try my best to try and think, as a Nepali citizen, why we should care about the sea level rise. We are a landlocked country, but why should we care about sea level rise? For me, it's a no-brainer because I consider myself as a global citizen, and it's a closed system. Our system is a closed system. So if you poke in one part of the closed system, then its impact is going to happen elsewhere, be it directly or indirectly. But I think one quick way I could think of is that I'm sure some of you have been involved in South Asian monsoon research, which I'm not an expert of. But my intuition tells me that warm and rising oceans might fuel the South Asian monsoon intensity and variability. And if you haven't done such research, I think it's time to investigate this problem with sincerity. And we know that I will have to tell you why South Asian monsoon is important for Nepal, because it is the lifeline of our water resources. And now you can extrapolate the associated hazards and socioeconomic impact of this process. And the second thing that I could think of is that, so we'll also have economic impact simply because $1 trillion damage to coastal properties globally because of sea level rise will directly impact the global economy. I mean, we have seen some wars happening as we speak now, and many other instabilities in global geopolitics, and associated economic changes and associated economic fluctuation will directly affect the way how we live our life on a day-to-day basis. And thirdly and finally, I like to call it humanitarian impact, because even though we are a landlocked country, so many of our neighbors, they have low-lying land, such as the one I show here for Bangladesh. And you could see this part of Bangladesh here, the elevation is already, elevation is nearly 1 meter, so it's below 1 meter. And if sea level is going to rise by 1 meter, this part of Bangladesh would be inundated. But when we talk about multi-meter sea level rise in the next couple of centuries, then we're talking about virtually on the greenish part of the country may not exist. And the similar story holds for Maldives. They have already started doing some conversations with other countries. I mean, I heard the rumor that they have been talking with Danish government to try and migrate their people to Greenland or somewhere there. But anyway, so we might have to deal with climate refugees, in particular sea level refugees from our neighboring low-lying countries. So it's a as it appears on the face of it, it's not our problem, but it is our problem, and it's better we start, thinking about this problem sooner than later. So with that, I will be happy to take any questions, and I really appreciate your attention and interest in my presentation. Thank you.
Thank you, Surendraji, for excellent talk. I think he showed us a very, the in-depth knowledge base of what's going on with the glacier changes and sea level rise, and he also looked at the small glaciers like AX010 and how it will disappear under different climate change scenarios, and multimeter rise of sea level projections, and then finally on the implications of the global ice change and also implication at the Nepal level. Now I'd like to open the floor for questions. Before I open the floor for questions, I'd just like to refresh those who are attending from the online social media platforms that we are in the middle of the YSFN talk series at Nepal Academy of Science and Technology here in NAST Hall. And those who like to have the connection and networking with the Surendraji, his visiting card is over there on the table. You can also pick that. Yeah, so question answers, so please raise your hands and if you have any questions. Okay, yeah. Please go ahead. No, do we have a mic here? I think it's a small hub, we can hear you.
No, I mean the virtual participant may not hear the question. Are they still?
We'll repeat the question.
Okay, that's fine.
Yeah. Please.
कम्युनिकेसन इङ्ग्लिसै हुनुपर्छ कि नेपाली
नेपाली भए नि हुन्छ।
सबभन्दा पहिले त डक्टर सुरेन्द्रलाई यो प्रेजेन्टेसनलाई म धन्यवाद दिन चाहन्छु। म उहाँको बीको ब्याचमेट पनि हो र हाल म प्रधानमन्त्री कृषि आधुनिकीकरण परियोजनामा सिनियर प्रोजेक्ट इन्जिनियरको रूपमा कार्यरत छु। जसको इन्जिनियरिङमा PhD गरेको छु र जसको इन्जिनियरिङमा मास्टर पनि हो। हामी चाहिँ ब्याचलर चाहिँ एग्रिकल्चरल इन्जिनियरिङ भएको नाताले म मिनिस्ट्री अफ एग्रिकल्चर एन्ड लाइभस्टक सेक्टरमा काम गरेर आउँछु। यो क्लाइमेट चेन्ज र एग्रिकल्चर र वाटर सिनेरीको बारेमा हाम्रो साथै केही अध्ययन छ कि यो क्लाइमेट चेन्जले गर्दाखेरि ओभरअल नेपालको चाहिँ एग्रिकल्चर सिस्टम अथवा नेपालको वाटर सिस्टममा कस्तो प्रभाव पार्नेवाला छ। हामीले पनि धेरै यो स्पेसली अहिले जुन परियोजनामा काम गरिरहेको छु यो परियोजनाको एउटा अब्जेक्टिभ चाहिँ क्लाइमेट स्मार्ट एग्रिकल्चर, क्लाइमेट चेन्जको चाहिँ इफेक्टहरूलाई चाहिँ कसरी कम गर्ने भन्ने हो। र हजुरको अब यो इन्टरनेसनल नलेजको आधारमा नेपालको कन्टेक्स्टमा केही छ हजुरहरूले अध्ययन गर्नुभएको अथवा केही भन्न चाहनुहुन्छ कि ताकि अझ राम्रो हुन सकौँ।
Thank you, JJ. The question is there any connection between climate change and agricultural stuff in Nepal? So unfortunately, I did not study the impact of climate change on agricultural business. And I think other colleagues, including Santos, might have done some work on the impact of climate change and glacier melting in particular on hydropower, irrigation, and so forth. But unfortunately, I have not been fortunate enough to find the opportunity to investigate, those sort of crucial issue of climate change. So I don't know what else I can say. But thank you, Gigi, for coming. I appreciate you being here.
Okay. Model answer. Yeah. Ask.
Namaskar, Sir. First of all, I think I would like to thank Dr. Surendra. I think it's very, such an illustrative presentation we really see, and it's very. And first of all, I'm very proud that from Nepal, I think you are doing such a marvelous work. When you saw that AX010, it reminded me of my time when we went to the scientific expedition in 1974 in Elachi, Award Glacier. That was the first glacier that was studied in Nepal in extensive way. So in that hidden valley behind the Adhikari, so after staying for 5 months there, so that was the lots of environmental studies and a lot of glacier inventory over that region. Then after that, I think a lot of work has been done by ISSM also in 2003, then 3, 4, and 5. Because I am also associated with the Asia Pacific Network of Global Research. So that produced the first glacier inventory in the Hindu Kush region, very extensively in the Tibet, Sikkim, and in Pakistan. So I think this reminded me, that this is the picture that we also posted in 1978 when we produced the result in the JPL journal. Now, we can talk a lot about, but coming to I'm curious about, since I'm working on the monsoon in Asia, when you saw that revolving globe below with the sea level height, what I see is east of the continuum, suppose the US or Asia, where you have the warm current like a Gulf Stream, Eurasian current, there I see the rising of the sea level. Does it imply that because of warming, is it only the thermal expansion that is responsible for that one? See, if you look at it, in the east side of the continent, I was just wondering,
Southeast Asia.
because when we did study in the Southeast monsoon or the Asian monsoon, because the driving factor is the difference between the temperature land and the sea. If the sea temperature is going to rise, then we are going to have a drastic change in the monsoon system. And of course, that is going to have a lots of implication in agriculture, water resources, and everything. So I'm just wondering, is there any study that has been done like this very extensively in the Indian Ocean region, Bay of Bengal and Arabian Sea? These are the places from where we get all these ingredients for the monsoon system. So I would like to, hold that question for you. Thank you very much.
Yeah, thank you, sir, for your question. And again, the short answer is I have not done any work on that particular problem, but I am definitely interested in maybe working with you guys on this problem. So what I have done, somehow relevant work that I have done along this line is computing what I call the fingerprints of sea level, which is basically trying to compute the equities. Maybe we have to use. Okay, so one the thing that I have done extensively is how the meltwater from glaciers and ice sheets is going to be distributed on a global scale, and of course including the regions that you have highlighted. And so we know that the bigger component of global sea level change is going to be mass related rather than the expansion of the ocean, and it will have some direct impact on on the dynamics of Southeastern monsoon. But again, yeah, I don't want to spend too much time to try and not answer your question, but I'd be happy to chat more about this problem, and hopefully we can work together in the future. Thank you.
Okay, two more questions. You first.
So, I have lots of questions, but I will ask only one. I have again contact with you later. So, these projections that you showed, I'm not an expert in this. My background is aerospace engineering, but I keep following because this is something that matters to all of us. So, these projections that you showed, how do they compare to the less conservative estimates, less conservative projections? Like for example, these are, and there are lots of projections. Some go much higher.